In the previous lesson, we learned that electric flux through a closed Gaussian surface is proportional to the net enclosed charge. Since this flux is proportional to the enclosed charge, we can say this flux is equal to a constant times the enclosed charge. To complete the Gauss law equation, we just need to find this constant. Since this is a constant, it should be the same for all situations with all kinds of closed surfaces. So we can just use the electric field produced by the simplest charge distribution and the simplest Gaussian surface to find this constant. What do you think is the simplest charge distribution? A single point charge would be the simplest charge distribution. Let's use a point charge positive q. To find the constant, we also need a Gaussian surface. It can be helpful for us to first draw some electric field lines. And the field lines come out of the positive charge. What is the simplest Gaussian surface we can make here? For this highly symmetric situation, we can make our lives a lot easier if we make use of the symmetry. There is a spherical symmetry, so a sphere would work great. To make use of the symmetry, the sphere must be centered on the point charge. Since we're looking for a constant, which should be the same regardless how big we make the sphere, I'm just making it like this with a radius r. Although I'm drawing a circle here, please remember that this closed Gaussian surface is a three-dimensional sphere, not a two-dimensional circle. The flux equals to the closed integral of E dot dA, and since this is a dot product, the dot product also equals to the magnitude of the electric field times the magnitude of the dA times cosine the angle between E and the dA. And I'm just going to rearrange this like E times cosine times dA because we're integrating E times cosine. In this integral, if there is any constant, we can take it out of the integration. Since we're doing a surface integral over the entire Gaussian surface, we can ask whether the magnitude of the electric field is the same everywhere on the Gaussian surface. Everywhere on the Gaussian surface, it is a distance r from the point charge. By symmetry or by Coulomb's law, which gives us E equals to kq over r squared, we know that the electric field indeed has the same strength everywhere on the spherical Gaussian surface. So we can take E out. Can we take out the cosine? Do we have the same angle between the electric field and the dA everywhere on the Gaussian surface? If we look at this little dA, the electric field goes radially outward, and the dA's direction is outward normal vector, so they are in the same direction, which means we have cosine 0 degrees. If we look at another dA, same, electric field is radially outward, the outward normal vector are in the same direction. So this is cosine 0 degrees. If we look at any dA around the surface, we get the same 0 degrees, which means the cosine 0 degrees is a constant we can take out as well. So now we have E taken out, and the cosine 0 degrees we take out, and all that's left in the integral is the closed integral of dA. What is the closed integral of dA? This is the dA, the magnitude over here. It is not the vector, and we are adding all the dA, the area, all the little pieces of area along the entire Gaussian surface, which means we get the total area of this Gaussian surface, which is the area of this sphere, the surface area of this sphere. So we have the E times cosine 0 degrees is 1, and the area of this entire Gaussian surface is 4 pi r squared. Oh, and of course, according to Coulomb's law, we know E is k q over r squared. So this times 4 pi r squared, the r squared cancel, and we get k times 4 pi times the q, and that q is the enclosed charge inside this Gaussian surface. So this is the same as the enclosed charge, which means what is our constant? It's k times 4 pi. So the constant we've been looking for is k times 4 pi, and we also know that this k here, it is also 1 over 4 pi epsilon naught. So if you multiply k by 4 pi, you get 1 over epsilon naught. For Gauss's law, we usually use this as the constant. So we can put this together. The flux through a closed Gaussian surface equals to the enclosed charge divided by epsilon naught. And this is the Gauss's law. In the next few lessons, we will learn how to use Gauss's law.